So we are going to start with a method called PILCO, which stands for Probabilistic Inference for Learning Control. Now, if you have worked with reinforcement learning before, you will know that most algorithms need a huge number of interactions with the environment. PILCO is different. It is model-based, and what makes it stand out is how little data it actually needs to start working. And okay, here. So instead of just letting the agent play around randomly and hoping it learns something useful, here the algorithm builds a model of the environment, and it does that using Gaussian processes, which are statistical models that can estimate both the expected outcome and how uncertain we are about that estimate. Okay, and the big advantage here is that you can get good results with far fewer interactions. That's especially important when you are dealing with real robots or physical systems where trial and error is not cheap or safe. And okay, let's take a look at the main structure of how PILCO is built. And at the top we have got the Gaussian process dynamics model, and what this part does is learn how the system behaves. It learns a mapping from the current state and action, so we write that as f of x sub t and u sub t to the next state x sub t plus 1. You can see here. But what's different here is that it doesn't just give us a single point as a prediction. It gives us a distribution. That means we are not only saying where the system is likely to, but also how uncertain we are about that. You can see training episodes count below this part. This tells us how much data model has seen so far. Okay, and that's okay. Then we move down to the policy section, and this is where the algorithm tries to decide what action to take based on the current state. The policy is written as here phi of x sub t theta. That just means it's a function that maps the current state to an action using some parameters theta. Okay, and this policy can be something simple like a linear controller, or something a bit more flexible like an RBF network. You can see here. Just below that you can see the number of policy iterations, which tells you how many times we have refined or updated the policy. Now between these two components, the dynamics model and the policy, there is this loop going on. So here is how it works. We learn the model, we use it to simulate possible outcomes, we optimize the policy using those simulations, then we apply the policy in the real world, collect new data and update the model again. This whole loop keeps going. That loop is what we call model-based policy optimization. Okay, and you can see here it is based on the idea that we can improve our actions using what we have learned about how the system behaves. And speaking of the real world, this part here shows the actual environment where the agent is tested. So we are not just training in simulation forever. Once the policy looks promising, we try it out on the real system. This could be anything from a pendulum to a robotic arm. Okay, and then finally we have got the simulated trajectories. These are imagined outcomes based on the model, not real data, and we use them to compute the expected performance of a policy. That's what we call analytic policy evaluation. We estimate the total cost or reward the policy would generate by running it forward through the model, including all the uncertainty. There is a list of the key components of PILCO, so let's just briefly go through what those are. The Gaussian process model is the part that learns how the system reacts to actions. It gives you both a mean prediction and an uncertainty. Then we have got policy evaluation, which estimates how good a policy is without needing to actually run it in the real world. Policy gradient optimization uses the evaluation results to update the policy in a direction that improves performance. And moment matching helps keep things tractable by turning complex, possibly non-Gaussian distributions into Gaussian ones. That way we can still do the math cleanly. And finally, uncertainty propagation means that we are not ignoring uncertainty, we are actually using it as part of the process when planning or optimizing. And uncertainty propagation is here. One of the key features of PILCO is that it doesn't ignore it. It actually carries uncertainty forward as it predicts what will happen in the next time step and the one after that and so on. So instead of saying at time step 1 the state is exactly this, we say there is a distribution over possible states, and the same goes for step 2, step 3, all the way up to the planning horizon. Okay, and in the notation here we have got p of x1, x2, dot dot dot, so on, up to p of x sub n, and each of those is a distribution, not a fixed value. Okay, there's a slider here that lets you control how much uncertainty is shown, so you can get a feel for how the model adapts when it's confident versus when it is not sure what's going on. Now, what does this give us in practice? Why do we care about modeling uncertainty? First of all, it helps avoiding overfitting to parts of the system that the model has not really understood well. So it avoids what's called model exploitation. The policy doesn't take advantage of prediction errors just to get a better score in simulation. Second, it lets us learn safely with less data. If the model knows it is uncertain, it can play it safe until it gathers more evidence. Third, it is useful for planning over longer time horizons. Okay, and if we ignore uncertainty, small errors compound quickly, but here the algorithm keeps track of how sure it is at each time step, and that's okay. And it allows also risk-aware decision making. So if a certain outcome is too uncertain or risky, the policy can take that into account and choose a safer alternative. So far, all of this sounds great, but let's step back and compare this this model-based approach to model-free reinforcement learning methods like PP or SAC. Okay, on the model-based side, the first clear advantage is sample efficiency. PILCO can learn good policies with 10 to 100 times fewer interactions. Second, it models uncertainty explicitly, which we have been talking about. That improves robustness. Okay, and the policy is optimized analytically. We are using gradients that come directly from the cost estimate rather than relying on trial and error or random sampling. And okay, there is a downside too. As the number of states and actions increases, things get more computationally expensive, of course. The Gaussian process model doesn't scale very well with big data sets or high-dimensional problems. On the other hand, model-free methods are more scalable. They can handle complex environments better, especially when you have got plenty of data. But they usually don't model uncertainty, and because they need to explore a lot more, they tend to require millions of interactions before reaching desired performance. Okay, so each site has trade-offs. PSO is great when you want to learn quickly and data is expensive, but you need to be okay with the added competition, and model-free methods are more brute force. They explore more and tend to be slower, but they work well in bigger spaces. And algorithm flow is here and training progress. Okay, what makes this method work so well is its ability to deal with uncertainty in a way that still allows us to do optimization analytically without running thousands of simulations. So what we are doing here is using Gaussian processes to model the dynamics of the system, meaning how the state changes from one step to next depending on what action we take. But more importantly, we are also using this model to predict distributions, not just fixed numbers. And here pseudocodes, what's happening here, and here GP dynamics model learning, okay, and here other things. The state at time t as written as x sub t, and the next state depends on the previous state, and the action which we write as x sub t plus 1 is equal to x sub t plus f of x sub t and u sub t. Okay, and the function f represents the dynamics, so it tells us how the system behaves when we take an action. But here's the thing, we don't know the exact form of f. That's why the Gaussian process model comes in. Instead of learning a fixed function, we learn a distribution over functions, which gives us a mean and variance. And the GP predicts both the most likely outcome and how uncertain it is. When we want to predict what will happen after multiple time steps, we need to carry the uncertainty forward. That's what we call uncertainty propagation. So let's say we have a distribution over xt. When we apply a function f to that, we don't just get a new value, we get a new distribution. And mathematically, we write this as p of x sub t going through the transition function to become p of x sub t plus 1. Then that gets passed again to get p of x sub t plus 2 and so on. Okay, and that is done. The thing is, these are all probability distributions, and computing the exact form of these distributions can get messy, especially because we are applying nonlinear functions. And I'm looking again. Okay, so what we do instead of so what we do instead is something called moment matching. What that means is we approximate these complicated distributions with Gaussians by matching the first two moments, that is the mean and the covariance. You can see the expected value term here, capital E of fx, E of x, okay, and also which stands for the mean, and then we also compute the variance, and with those two we can build a Gaussian that approximates the true distribution. It won't be perfect, but it is good enough for us to do further calculations. Okay, that is done, and again I'm looking here. So how this fits into the policy optimization? We are interested in minimizing the expected cumulative cost. We usually write that as j of theta. This is a function of the policy parameters theta, okay? And the goal is to find a policy that maximizes j theta, which is defined as expected sum of costs over time. So j equals the expected value of the sum over time of c of x sub t. The cost function here tells us how bad a certain state is. This could be a distance from a target, energy usage, deviation from some desired configuration, or whatever fits the task. And okay, what makes this work is that we can take the gradient of this expected cost with respect to the policy parameters. That gives us a way to improve the policy using gradient descent, which is more efficient than using random sampling. And remember, all of this is based on the GP model of the dynamics. We are not doing this by running a bunch of rollouts in the real world. We are using our probabilistic model to compute everything. And okay, we model the transition dynamics with a Gaussian process here. Okay, and then we use moment matching to approximate the predicted state distribution as Gaussian, so we can keep things tractable. And here you can see our GP kernel function and training GP model. Here our uncertainty visualization, and you know advantages of PILCO. Here sample efficiency, uncertainty awareness, you know that analytic gradients, automatic regularization, principal exploration, and you know flexible cost functions. And you know they, and for real world applications, here we can say it is used in robotic control tasks, autonomous systems, industrial control, and healthcare applications. And if you want to learn or search, here's other variants or extensions, for example deep PILCO, safe PILCO, multitask PILCO, or variation inference approaches. And that's okay, our formula is here, and I think that's enough for this PILCO. And if you are interested, you can search it in Google. Okay, that's all for this lesson then. See you in the next class.